Hello everyone. So let us study the next type of problem. It's again a three-hinged parabolic arch, but this time it has only a UDL. Okay, you can see here there is only a UDL on the left span. Okay, so first let's draw the figure. So it's a three-hinged parabolic arch. So it's 1, 2, and 3-hinged parabolic arch of span 30 meter and rise 5 meter, and carries a UDL of 20 kilonewton per meter over the left span. So only left span means it is between A and C. There is a 20 kilonewton per meter UDL. And okay, so you have to determine the support reactions, N, Q, that is normal thrust and radial shear of 5 meter from both 5 meter both from the left support. Okay, from 5 meter from this you have to find N and Q. Now in addition to this, you're supposed to find the magnitude, position of the maximum positive and negative bending moment. Okay, you have to also find positive bending moment, negative bending moment. Okay, now this, just by seeing the figure only, you can make out wherever there is loading there will be maximum bending moment, and wherever it is unloaded, okay, in this portion it is unloaded, there are absolutely no loads, so in this portion it undergoes negative bending moment. So that's why you have to find maximum positive, maximum negative bending moment. So maximum positive will be in this portion AC, because there's a loading, external loading, and there's negative bending moment in portion BC. Okay, so as usual, again start with the first thing, that is support reaction. So support reaction as usual. So at A and B there are hinge support. Remove the support and show with the reactions. So hinge support only two reactions, HA and VA. At B, HB and VB. Okay. Then first use the equilibrium equation. Summation H is equal to 0. Summation V is equal to 0. Moment about A is equal to 0. And there are four equations. To solve the four equations, you have to use the fourth equation, that is moment about C is equal to 0. Okay, so first summation H is equal to 0. So HA right side, HB left side. So HA plus minus HB is equal to 0. Next, summation V. Summation V, vertical forces. VA plus VB minus 20 into 15. So 20 into 15 is equal to 0. So this load is acting downward. So VA plus VB is 300. Okay. Next, moment about A. Find moment about A is equal to 0. So moment about A is equal to 0. So in this portion you can see A equal to 0. So VB into 30. So it's going anti-clockwise. So minus VB into 30. Next, load, this load. So 20 into 15 by 2, because it's a UDL, is equal to 0. HB and HB will not occur because it is on the same line of that of A. Okay, so there are only two loads, this and this. Okay, so we'll get the value of VB. When you get the value of VB, substitute in this equation, then you'll get the value of VA. So we got to know VA and VB. Next is moment about C. So moment about C in span AC. Okay, I'll take moment about C in span AC. Okay, so why I'm taking this here, because if I take it here, it will have more importance because AC is loaded. That's why I'll take an left side of the span. Okay, so now we got to know VA and VB. So left side, VA is acting. So it is VA into perpendicular distance. So VA, that's 225 into perpendicular distance. It is 15. So left side, clockwise is positive, anti-clockwise is negative. So this is clockwise positive, anti-clockwise. So this is going like this, anti-clockwise. 20 into 15 into 15 by 2, anti-clockwise. Then now HA, because we're finding moment at this point. So HA is also going anti-clockwise. So it's minus HA into height, 5. So all this you'll get HA. Then once you get HA, put it back in this equation here. We'll get HB. So we got to know all the unknowns, VA, VB, HA, HB. So whenever you find these answers, just box them. Things become simpler for you to use further. Okay, next, once you find the reactions, find the resultant, Ra, Rv. So Ra is equal to square root of Ha square plus Va square. Okay, put these values here, Ha, Va, and theta is tan inverse of Va by Ha. Similarly, Rb is Hb square plus Vb square. Solve this, and then theta b is tan inverse of Vb by Hb. Okay, so you get theta A and theta b. Next, find the bending moment. Okay, so we know that bending moment is 0 at A, C and B because these are the hinge support. Bending moment at the support is 0. Next, because it's a 3-hinged parabolic arch, we have the equation that is y is equal to 4h lx minus x square divided by l square. So put all the values here. Okay, so you'll get the value of y. So y is equal to 0.67x minus 0.022x square. Okay, so this equation will be using further. Okay, so now we know that bending moment would be obviously maximum at the in portion AC because it is loaded. Now if it's a point load, we'll get to know that just below the point load bending moment is maximum. But this time there is only UDL, so you don't know exactly at which point the bending moment is maximum. So what we'll do is, under such situation, we'll first locate a point for this UDL. Okay, not necessarily it will be exact. So if it is 15, not necessarily it will be exact 7.5. It's never like that. So what we'll do is, we have to find this x distance. We have to find this x distance, that is because of this UDL, where is the maximum bending moment occurring. Okay, so to do this, we'll use this equation now. See here, 0.67x minus 0.22x square is y. So this y is the parabolic equation which I've solved. This y means vertical distance. Okay, now to find out the maximum bending moment in portion AC, so what I'll do, let x be the distance from A. So I'll cut this section, let x be the distance from A. So I'll imagine that at this portion, the bending moment is maximum. So I have to find at what distance of x. So if I cut the section here like this, I'm cutting the section here. So if I cut the section here to the left side, check how many loads. VA, HA and this portion, only this portion. Okay, so what I'll do here is, to the left side, I have to find maximum bending moment. So I'll write it as MX. Okay, so MX is nothing but cut portion to the left side. Okay, so MX is equal to VA, 225 into x, perpendicular distance. Next, HA is also 225. So 225 into y, and this 20 into x by 2. 225 into x minus 225 into y minus 220 into x by 2. Okay, so now in this equation, see here, 225 into x, I'll write it as it is, 225. Okay, in place of y, I'm going to replace this because I already know y in terms of x. So y is, put it here, 0.67x minus 0.022x square. Then, so put this. Okay, now everything is in the form of x and x square. So you can solve this. So once you solve this, you'll get the equation of bending moment. Okay, so this is the equation of bending moment. But our main intention is to find out at which point of the UDL, from the left support is the bending moment maximum. We just know that it is maximum in AC, but we have to locate at which point. Okay, so if you look at which point, so it is, what we'll do is, we'll use this equation for bending moment to be maximum. We'll take the bending moment equation, we'll take the derivative of that. So dou m by dou x is equal to 0. So dou by dou x, I'll take it out, and then in this m is nothing but the bending moment equation what we have got here. So this equation we'll put in here, that will equal to 0. So now solve this. So it is 74.25 minus, okay, 2, bring it here. So 2 into 5.05, x is equal to 0. So now we'll get the value of x. You can see here, x is 7.35 meter. So this x is 7.35 meter. Okay, so at this 7.35 meter from the left support, the bending moment is maximum. Okay, so now we got to know the value of x. So we'll put it back in this value, we'll put it back here and check how much is the maximum positive bending moment. So mx is equal to, now same this equation, instead of x put this value, then 5.05 right here, and x 7.35 square. So now we'll get bending moment maximum, that is positive. Yes, positive bending moment. Okay, now why we say it a positive? Because in span AC, the beam is loaded, the arch is loaded. So of course, whenever there is a loading happening in that particular span, there will be maximum bending moment, and more specifically, maximum positive bending moment. Okay, next. Now, next thing is you have to find maximum negative bending moment. So now maximum negative bending moment will occur in the no loading portion. So no loading portion is here, the CB. There are absolutely no external loads. So here there will be a maximum negative bending moment. Okay, now how to find out this is same thing. We know, we'll put it first, find the bending moment equation here. So bending moment equation, so I'll cut this section here. Now same thing what we have done here, the same thing. So I'll cut the from B portion, from point B, x, and this is y. So there are only two forces occurring here. So if I cut this portion here, to the right side there are only two forces. So again, right side anti-clockwise positive, clockwise negative. So it is 75 into x, next 225 into y. Okay, I've used it here, the same thing. 75 into x minus 225 into y. So 75x, right as it is, 225. Now we already have solved the equation of y. So put it back here and solve this. So now you'll get bending moment equation. So it is mx is equal to minus 75.75x plus 4.95x square. Now this is the equation you have to use further. So this equation you can see here, for bending moment to be maximum, differentiate m with respect to x. So dou m by dou x should be equal to 0. So again use this equation now. Okay, dou by dou x, in place of m, put this equation. Okay, so it is minus 75.75. Okay, plus this x into 4.95. X into 4.95 is 9.9x is equal to 0. So now x is equal to 7.65 meter. So the meaning of this is, from B, if you measure x as 7.65 meter, the bending moment would be maximum. And more specifically, it is the negative bending moment. Okay, so put this value, take this value and put it back in this equation, bending moment equation. Okay, so now bending moment would be minus 75.75 in place of x 7.65 plus 4.95 into 7.65. So see, because it's a negative, so you get a negative answer. So bending moment is negative. So this is nothing but maximum negative bending moment. Okay, so you have found out all the parameters now. So what you have to do is again draw the bending moment diagram. Okay, now look at this, how to draw this. So ACB, now this is like a zero line. Okay, zero line. So whatever you draw above would be positive, below would be negative. Okay, so now in AC portion it is positive. Now at what distance? 7.35. So from A, 7.35, mark this point. It is 272, maximum positive bending moment. Similarly, BC. So in BC portion, okay, so in BC portion, because it's a negative, so I'll mark it below this line. So this is like more or less like a zero line. So whatever you draw above positive, so below the zero line in that portion would be negative. So below this at a distance 7.65, this is negative. Okay, that is 289. All right. So once you mark this, next is you have to find calculate normal thrust and radial shear. Now again, the question they have asked to find normal thrust and radial shear at a distance 5 meter, 5 meter from the left support. It means at a distance, the total length is 30 meters. So at a distance 5 meter from the left support, you have to find the radial shear and normal thrust. Okay. So now we'll cut this section. Okay. So at this is like A, HAVA. Okay, and 5 meter mark like this. This is dx dy and complete this arch. Okay, and then there is a UDL within this span. There is also external load UDL. Okay, now see here VA 225, HA 225. We have marked this because these are the reactions which we have already found out. Okay, now to balance these, there should be equal and opposite reaction at this portion. Okay, now see here, this is horizontal force 225, right side. To stop this, there is equal and opposite force 225 acting to the left side. Okay, this is balanced. But there is an additional load of UDL which is trying to push this part of the arch downward. So what we do here is, first thing is 225 upward. So here also 225 downward. But because there is also a load acting in between the span from 0 to 5 meter, so 225 minus 20 into 5. I'll consider this portion of a UDL load. So this UDL is 20, which is acting over a span of 5. So it is 20 into 5. So now 225 minus, you have to minus this load always. 225 is this. Upward, here also it is downward. So 225 minus 20 into 5. So it is 125. Now this is the actual vertical force V which we'll be using here. Okay, now this becomes V and this becomes H throughout the problem. Okay, so now once you find out this, then you find out the angle here, theta. So we know that tan theta is dy by dx. Okay, so we know that tan theta d by dx will write here, and we also have calculated the equation of y. So y you have written here. So at x is equal to 5 meter. Okay, solve this equation. D by dx, solve this equation. So theta is equal to now 24.22. Okay, now this is a theta you have to put in this equation. So use this theta and find out sine theta and cos theta, which we can use it directly here. Okay, so V is 125. Okay, so again for the equation N, normal thrust, it is V sine theta plus H cos theta, and Q is just the opposite. V remains V, H remains H. Sine becomes cos, cos becomes sine, followed by the change in the signs here. Okay, so V is 125 sine theta, H is 225 cos theta. This is N, and Q is V, just the opposite, minus H sine theta. Substitute. The main important thing here is you should never forget to consider this. So if it's 225 here, 225 minus the external load which is acting in that particular span. Okay, so with this we find out normal thrust and radial shear. Okay, so the only different thing about this problem is, in addition, because there is no loading here, there will be positive bending moment, positive, positive maximum bending moment, positive, and to the right side of this, that is see no loading condition, so there would be a negative bending moment. That is what you have to consider properly and solve it into equations. Okay, that's it for today. Thank you.